Hello, my name is Vicky and I am an astronomer and a science communicator, and I work for RAL Space, the UK's National Space Laboratory. Today I'm going to take you on a virtual tour of our facilities to show you how we bring a space mission or a space project to life. And of course this wouldn't be possible without all the teams of people who bring together their different skill sets and different backgrounds to collaborate to make these projects successful. And I'm going to mention a few of these different types of jobs, these different roles just within RAL Space and across the space sector as well, and give you an idea of how these people got into those roles. This virtual tour is available online. Anyone can access it from the RAL Space homepage. This is our main building. We are based at the Rutherford Appleton Laboratory in Oxfordshire, and we have a few partner sites across the UK as well. Inside, we can see quite a few different information points along the tour, so there's more information you can go and find out if you would like to. And just inside here, we can actually see our timeline of RAL Space. So I can zoom in a bit here. So you can see that we've been involved in lots of space missions. We've actually been involved in over 200 instruments, that's components that are on spacecraft, that have been on board spacecraft and into space. And we've been involved in missions over the last 60 years now. So we've got a lot of heritage, a lot of expertise across different things. And at RAL Space, as the UK's National Space Laboratory, we are involved in almost any stage of a space mission. So that can be from thinking of new missions, new concepts for missions, trying to solve problems for us on Earth, or challenges that we need to solve. What new space missions do we need? So we propose new missions. We help with the design of the hardware itself. And then we have our facilities, especially in this building, where we can assemble everything, build it, put it all together. And then, most importantly, we help to test spacecraft and space hardware. Testing is absolutely crucial to make sure that everything can survive the journey into space and can survive its lifetime in space. Once it's in space, of course, we want to get all the data back, or if we're working with observatories across the Earth as well, we want to get the data from those. And we have a team called the Centre for Environmental Data Analysis, and they help to run Jasmine. Jasmine is a supercomputing infrastructure. Jasmine has about 45 petabytes of data storage capacity. It's incredible. And we help to store all of this data, pictures of Earth for satellites looking back down at Earth for Earth observation. We can take that data, those measurements, and we can store it on a supercomputing infrastructure, and we can share it with scientists across the world for different research purposes. So those are all the different stages that we can support. We do almost everything except the launch. And this is where we can collaborate with our partners nationally and internationally with different space agencies to make a whole space mission and bring that to life. We're also involved in lots of different types of things that go on. So we can look at solar missions, looking at the sun. We can be supporting Earth observation missions, as I mentioned, especially now more than ever, really important to be monitoring our climate. We support communication satellites, navigation, and also astronomy as well. And this actually is a model of MIRI. So MIRI is the mid-infrared instrument. So it looks at infrared light, thermal images. You might think of a thermal camera. And this is on board the Webb telescope, which launched on Christmas Day in 2021. And we helped to do all the thermal design for MIRI. So we helped to check that, we helped to design it, and we helped to test it. And we've got a model here. And Webb will be sending back lots of incredible images of galaxies taken with MIRI. In here we have one of our event spaces. This is where we can host a lot of events and visits, and also it's a space for collaboration. And we've got some windows into our clean rooms and labs, which we'll have a look at a little later on. But just around here, I can show you an example of a career profile. So we have lots of career profiles on this tour, so you can meet some of our people and find out how they got into the space industry. So this example is Melissa. She's a project manager. So project managers are responsible for making sure that any space mission or project we're involved in delivered on time, delivered to the right budget, so within budget, and that it's really high quality. So Melissa actually studied chemical engineering at university, and she really enjoyed working on group projects to solve a problem. And she found that her skills were in communication and organisation. She could bring a whole group together, lots of different ideas and objectives, and bring it all together into a unified project to find the best solution and the most efficient solution as well. So she really enjoys being a project manager, and that's one example of a career in the space industry. Another example of the jobs we have at RAL Space are scientists, research scientists. So here we've got an example of an Earth observation mission, Sentinel-3. Now the Sentinels, they're a whole family of Earth observation satellites, so they're looking back down at Earth, and Sentinel-3 in particular has an instrument that's looking at measuring the temperature of the surface of Earth. So it measures the temperature of the land and the oceans, and that's especially important to monitor global warming. So one of our scientists, Caroline, she is a scientist who analyses all that data, and she also uses her problem-solving skills to investigate how we can improve the accuracy of that data, especially when we're measuring it over such a long period of time. So Caroline studied physics. She did physics at school and at university, and as well as just writing research papers and things, she really enjoys being part of the space mission and getting to see how to improve satellites and the data that we collect from them. In here is our control room. So this is where we control all our facilities, our big scale facilities, for all our assembly and testing of spacecraft. And you can see lots of different monitors in here for monitoring all the data. And one of the examples of a role here is John, one of our senior systems engineers. He started as an apprentice. So we've seen a couple of examples of people who've done a degree at university, maybe even a PhD, and then got a job in the space sector. John actually had an apprenticeship first, so straight from school he went to do an apprenticeship, and then he had different work experiences in different industries, and then came into the space industry and applied his skills from other sectors to the space industry. So a systems engineer is bringing together all the different types of engineers into one project. So you might have thermal engineers, electronics engineers, mechanical engineers. The systems engineer looks at the whole system to make sure everything works and is compatible with each other. So that's an example as well of applying skills from a different industry. We also have in this area quality assurance and product assurance teams. So especially when we go into space, we need to make sure that the quality of the data, those images we get, is very important. So of course the quality of the hardware itself needs to be very high. So our quality assurance teams make sure that the facilities are all up to scratch, and our product assurance teams make sure that the hardware, the products that we build, are what they should be as well. And our product assurance manager, he actually did history at school, and he studied ancient history at university, and his skills in looking at lots of different information, different sources of information, and his attention to detail is really critical to pick up any slight defects in hardware, for example, down to the nuts and bolts that we use on the spacecraft, looking at the processes, making sure everything is working as expected. Our product assurance teams are also really important. So now we can go into some of our facilities, and I've mentioned some of our clean rooms. So I'm going to show you inside one of our clean room changing rooms. Looks like any other changing room. We come in from our offices into this space. We get dressed in clean room suits, and then we can cross over the threshold. We can step over this bench and go into the labs. And I can show you a picture of me in a clean room suit, so all dressed up here, head to toe, completely covered. We're quite used to wearing face masks when we work in the labs. We have gloves, we have hairnets and hoods, and big overshoes as well. And the reason we have to use clean rooms for when we are assembling all our hardware is so that we don't get any dirt on it. So if you imagine if you had a dirty fingerprint on your camera, you would get a blurry image. So that would affect the quality of data we get, especially if it's a space telescope. And once something's sent into space, it's very difficult to change anything. So if you had a dirty thumbprint, for example, on your camera, you can just wipe it off. But once it's in space, we can't just fly up there and wipe off a dirty thumbprint. So that's why we make sure to build everything in clean rooms and quality check everything as we go along. And the dirtiest things that go into the clean rooms are us, humans. We can shed fingernails, skin, hair, anything that can fall off us So we wear these clean room suits and we have to also walk quite slowly through the clean rooms so that we don't pick up any dust and transfer it to somewhere else. So there's quite a few rules when we go into the clean room. So let's have a look inside. Inside the clean room, you can see we've got a big white space here, some windows out to the corridor we saw at the start, and this is where we can assemble our spacecraft. You can see we've got these big vents at the bottom, so we really control the conditions of the air in there, so we can control the temperature, the pressure, the humidity to make sure it's all at the right standard and reduce the amount of particles in the air as well so that nothing can contaminate our hardware. We have a little traffic light system, you can just see that on the wall there, and that's again to make sure that the quality of the conditions in there, the cleanliness of the room is what it should be. So we're on green, so we're good to go. We would get a warning light if anything wasn't as it should be, and then we could step out, clean everything, reset, and then continue work. I'll just point out in this clean room as well, another career profile we have, another systems engineer, this is Kim, and she actually started off doing physics first. She did physics at university as well, but then she decided she wanted to apply her knowledge to something else. So although she did physics, she actually applied for an engineering job. So you can transfer different skills from physics to engineering, especially if you have math skills. They're very applicable in different situations and different roles. So once we have hardware that is built, and maybe we might do a model of a spacecraft first before we go on to the real thing, we need to make sure we test it. So one of the tests we do is vibration testing, and this is to simulate a rocket launch. If you've ever seen videos of a rocket launch, or maybe one in real life if you're very lucky, it's a very violent experience, lots of shaking, lots of vibrations. And of course, that can be very risky if we've got delicate equipment in there. We've spent so long being very careful, building it in the clean rooms. Again, we want to make sure that it can actually survive that journey into space. So what we do is we have this big shaker table. We put our hardware onto this table and we shake it. It's actually a bit more accurate than that. We can actually match the vibration profile to a specific launch vehicle. If we know it's going on a NASA rocket or SpaceX or anyone else, we can try and match that profile for what it will experience when it goes into space. And we can look for any resonant frequencies, any weak spots, and see if anything breaks. If it does, back to the drawing board so that we can make sure it's the best quality before it goes into space. And I'll just show you a video of this in action. So this room in here is actually on its own seismic block, so it's isolated from the rest of the building. If we were stood outside, we wouldn't be able to feel these vibrations. But our teams of technicians and engineers can monitor what's going on from the room just behind. And it does get faster and faster and faster, up to the point where we can only just about see that it's still moving. It still is, but that's because the frequency of vibrations is so high. Another test that we can do in here is pyroshock, so we can simulate any shocks that our space hardware might experience. In particular, during a rocket launch, you can often see when there's rocket stage separation, so when the nose cone comes off or the boosters come off, different parts of the rocket separate. Each time that happens, there's a jolt. And again, especially if we're looking at CubeSats and constellations of satellites, there's a little jolt to send each CubeSat out. Again, there can be jolts there. So we use this pyroshock simulator to fire a projectile at our equipment with a buffer plate in between and see if it survives. So now that we've simulated a rocket launch and made sure that it can survive the journey into space, we actually want to see how it's going to fare in space when it's up there. Now, space is a vacuum, and the temperatures in space can vary as well. So what the spacecraft could experience could be very, very hot when facing the sun, or very cold when facing out into deep space. And if you imagine our electronics, they don't tend to like those temperatures at the extreme ranges. So we need to make sure that when we protect it, the hardware we build around it, that we protect it and it can all survive in those conditions in space. So we have space test chambers. We have 11 chambers in total of varying sizes that we use depending on whether we're testing smaller individual components or larger instruments up to an entire satellite. So this chamber here, this one's about 5 meters tall, so just slightly taller than a double-decker bus. You can see the people in here for an idea of scale. And in this chamber, we can roll in our spacecraft, we close the doors, pump out all the air to make a vacuum, and then we can control the temperature from the control room. So all these black panels around the edges, we can change the temperature of each one individually if we needed to, so that we can simulate temperatures you'd feel facing the sun or facing deep space, or in Earth's shadow, and we can simulate temperatures between minus 180 and plus 150 degrees Celsius. We have technicians who work on these chambers as well, and quite a few of our technicians have also done apprenticeships with us, and they've then built up their experience to go from an apprenticeship to then do a degree. Now, I mentioned we might need to protect our spacecraft, we might need to protect the electronics as well inside. So we need some insulation, and we use something called multi-layer insulation, MLI for short, and we make this in-house. We have a special lab where we can make this, and we partly make it by hand. We use CAD software and drawings so that we can have the exact dimensions of the spacecraft, and then we can cut some of it out by hand. And it's made of very thin reflective layers. It's aluminium coated plastic, and in between there are netting spacer layers, and that's to prevent any heat conduction between the layers, to prevent any heat transfer. So we can see what it looks like here. And one of the technicians who works in here, this is Ruben. Ruben uses his hands-on practical skills to make something by hand, and he talks about how rewarding it is to actually make something with your own hands that can end up in space, which is really, really exciting. He actually started off working for a medical company, so again, he was in a different type of industry, using different skills there, but he was working in a clean room environment, similar to our clean rooms. So he's quite used to working in those conditions and could apply that approach to working to be really accurate, really hands-on technical skills to work in our clean rooms and make these spacecraft thermal blankets, these MLI blankets. Another member of the MLI team, she had her own crafting business first. So she had a different background altogether as well, and from those crafting skills she could apply those again to make these spacecraft thermal blankets. So completely different ways of getting into the space industry, from apprenticeships to degrees to actually applying skills from different areas of life. And another example of this is one of our project managers studied geology, and actually she got a lot of skills from her extracurricular activities. So she ran her football team when she was at school and then at university as well, and that experience of managing the team and having to use actually project management skills when she was there to get sponsorship and to manage matches, she uses those skills and applies them as a project manager now. So a couple of other jobs we have are electronics engineers. We also have our operations team, so they are sending commands to spacecraft. We have our software developers as well, so data scientists who are looking at all that data on Jasmine, and all the software developers as well who are supporting new observatories across Earth, on Earth as well. And we also have all the other teams who are essential to making the organisation run. So all our business support roles in administration, our business development team and marketing, communications like myself. So I actually combined my skills from physics and studying astrophysics, as well as languages, to be able to communicate science. We also have our finance teams, our HR teams, and many more people who are essential to actually make these space projects happen. We do offer quite a range of options for people to get involved. So we have work experience for students from year 10 to year 13. We have placements for university students, so that can be a year-long placement or a summer placement. And we have graduate opportunities as well. But I would say definitely where skills can come from is not just the subjects, your STEM subjects, particularly math skills are useful, but also those extracurricular interests. And what we're looking for, especially in the space sector, is that collaboration, that teamwork, and also a willingness to learn. A lot of the things we're doing haven't been done before, so we are definitely pushing the boundaries of what's been done before and learning on these things. So willingness to learn and how you can apply your skills from anywhere is really important, especially looking to the future. And one of our new facilities, the National Satellite Test Facility. This is a one-stop shop for large-scale testing, and it's been designed so that it can test even larger spacecraft, up to the size of a minibus and up to 7 tons. And we'll be able to do all the testing in one place, and it will help the growth of the UK space industry. And these are all the new capabilities of the NSTF.
How to test a satellite for a lifetime in space in 8 easy stages. Before launch, every satellite needs to be scrutinized and tested to make sure it can withstand the rigors of the journey into orbit and works perfectly for its lifetime in space. At RAL Space, we test spacecraft from the size of a toaster up to the size of a minibus. We do this in 8 stages: clean rooms, vibration test, acoustic test, pyro shock, center of gravity and moments of inertia, thermal vacuum test, electromagnetic compatibility, antenna measurement system. Test 8, clean rooms. Before we begin to test, we make sure our rooms are super clean, so that there can be no interference with the satellite. Test 7, vibration test. We also simulate a rocket launch through repetitive violent shaking. A satellite needs to be strong enough to withstand huge forces as it blasts into space. Test 6, acoustic test. Launching into space is extremely noisy, so we simulate the acoustic environment during launch and measure how the satellite responds. Test 5, pyro shock. A satellite separates from its launch vehicle using explosive bolts. It will experience a shock from the jolting action. We test for how it withstands that too. Test 4, center of gravity and moments of inertia. We test the mass properties of satellites by gently wobbling it to find out where its balance point is and how it spins. Test 3, thermal vacuum test. Space is a harsh environment to work in. We test to make sure a satellite can work in severe temperatures and vacuum conditions. To do this, we put each satellite in a large vacuum tank and subject it to huge temperature extremes from -178 degrees Celsius to +120 degrees Celsius. Test 2, electromagnetic compatibility. Each satellite is put through its paces inside an electrically clean environment, allowing us to accurately measure electromagnetic emissions and make sure that external signals don't interfere with the satellite's operation. Test 1, antenna measurement system. AMS measures the performance of antennas used to communicate between satellite and the Earth. A satellite will face many hazards during its operational life. RAL Space makes sure that it's tested to the extremes, ready to face the difficult journey into orbit and carry out its mission for us all back on Earth.
So that's a snapshot tour of RAL Space. I hope you've enjoyed it, and I hope you enjoy the rest of STEM Clubs Week.